Something really incredible is happening in the world of robotics right now. For something like 60 years, we've been trying to get robots out of the factory and into our messy, unpredictable world. And for just as long, we've basically been hitting a wall. But a fundamental shift in thinking, a whole new approach, is finally starting to break that wall down. So let's dive into what this revolution is all about. Just look at the sheer variety of robots we're talking about today. We've got these super precise manipulator arms, we've got four-legged robots that can navigate all kinds of rough terrain, and yeah, we've even got full-blown humanoids. The challenge isn't just building these incredible machines, it's how do you teach all of them how to operate safely and effectively in our world? A world that, let's be honest, doesn't come with a neat instruction manual. And this idea, this single quote from reinforcement learning pioneer Richard Sutton, is right at the heart of this great robot reboot. See, for decades, we tried to perfectly model the problem, all the physics and complexities of the world. But now we're realizing it's way more effective to let the robot learn to approximate the solution on its own. It's a huge philosophical shift, so let's unpack what it really means. All right, so to really get why this new way is such a big deal, we've got to look back at how things used to be done. For the longest time, robotics has operated with this idea of explicit instructions. Think of it as programming a robot with a very, very detailed manual for every single thing it might ever do. The best analogy is that the classic approach is like giving a robot a flawless IKEA manual, right? Every part, every screw, every possible step is perfectly described. And if the real world matches that manual exactly, it works beautifully. But what happens when you drop a screw? Or the diagram is just a tiny bit off? The whole thing just falls apart. This old-school approach is called explicit modeling. It's where engineers use these incredibly precise mathematical formulas, like kinematics, to calculate every single movement down to the millimeter. They are literally trying to write the rulebook for reality, pre-programming every single action the robot can possibly take. And that right there brings us to the core issue. The real world is nothing like a perfect IKEA manual. It's messy, it's dynamic, it's full of surprises. And this mismatch between the perfect manual and messy reality creates four huge show-stopping problems for that classical rule-based approach. Problem number one, these systems are just incredibly brittle. You have all these separate modules for seeing and for planning and for moving, and they're all kind of bolted together. So if one part makes one tiny mistake, just one little miscalculation, the whole chain reaction fails. Game over. Second, the real world is a fire hose of sensory data, right? You've got cameras, mics, depth sensors. It's all coming in at once, and these classical robots really struggle to make sense of all that messy, high-dimensional information simultaneously. It's just too much. Third, the math is never quite perfect. The models just can't capture all the complex physics of the real world, things like the squishiness of a piece of fruit or the specific friction of a towel. And these tiny inaccuracies in the model, they lead to big, catastrophic failures in the real world. And finally, and this might be the biggest one, this old approach has no way to learn from experience. It's totally unable to tap into the massive data sets that are driving literally the entire rest of the AI revolution. It's a dead end. So you can see how these four issues, these brittle systems, the messy data, the inaccurate models, and the complete inability to learn, they've basically created a wall, a fundamental set of roadblocks that have kept robots stuck inside cages and in controlled environments for decades. So, how do we break through that wall? Well, let's go back to our analogy. Instead of giving the robot that perfect manual, what if we just gave it a box of Legos, and we let it learn how to build things through trial and error, through experimentation and observation? This is the core idea behind the whole new paradigm, robot learning. And this slide just lays it all out, crystal clear. On the left, you've got classical robotics. It's all about that explicit, human-written model, and it's super fragile when things change. But on the right, you've got robot learning. It uses implicit models that are learned directly from data and interaction, which makes it far, far more adaptable and robust. Now, the engine that's driving this entire new approach is a really powerful technique from machine learning called reinforcement learning, or RL for short. In a nutshell, it's a way for a machine to learn through trial and error, guided by a simple system of rewards and penalties. At its heart, reinforcement learning is a really simple but incredibly powerful feedback loop. The robot, which we call the agent, takes an action out in the world. It then observes what happens because of that action, and it receives a reward signal. Positive for good outcomes, negative for bad ones. Simple as that.
So it really just boils down to these 4 simple steps. 1, the robot tries something. 2, it observes what happened. 3, it gets a reward score, like a point. And 4, the important part, it updates its internal strategy to be just a little bit more likely to do things that lead to high rewards in the future. It literally learns from experience.
So if robots can learn just by trying things, you might see the catch. Training this way in the real world is painfully slow and, frankly, can be pretty dangerous. Can you imagine a giant robot arm just flailing around for thousands of hours to learn how to pick up a cub? It's just not practical. The obvious solution, of course, is to train it in a simulation first, where you can run millions of trials super fast and safely. The problem is what a robot learns in a clean, perfect simulation often doesn't transfer to the real world. These tiny, unmodeled differences in physics or lighting or textures create what researchers call the reality gap. So the holy grail, the crucial piece of the puzzle, is finding a way to learn in the real world, but to do it safely and efficiently. And this is where a truly groundbreaking new technique comes in, one that combines the robot's own learning with direct guidance from a person. This new approach is so effective because it combines 3 really powerful ingredients. First, it doesn't start from zero. It learns from watching experts. Second, it figures out what success even looks like on its own, just from a picture. And third, and this is the real game changer, it allows a human to jump in and correct the robot's mistakes while it's training. What you're seeing here is basically how it all fits together. This system creates this incredibly smart feedback loop. The robot is constantly learning from 3 sources all at once: a library of past successes, its own live trial and error, and direct corrections from a human supervisor. It's this combination that lets it learn so incredibly fast. And this is the magic ingredient in action. The human isn't puppeteering the robot the whole time. They're just watching. And when the robot is about to make a mistake, they can just physically guide it back on track. These little targeted corrections are incredibly valuable data points that completely supercharge the learning process. It allows these robots to master really complex tasks with near-perfect success in just 1 to 2 hours. It's amazing. So, what does this all mean for the future? Well, we're witnessing a monumental shift. We're moving away from painstakingly programming robots with these rigid, brittle rulebooks, and we're moving towards a future where we can teach them new skills interactively, almost like teaching an apprentice. And that makes the whole field of robotics way more scalable, adaptable, and honestly, a lot more accessible. And this brings us to a fascinating final thought, one that just opens up a world of possibilities. If robots can learn complex, real-world skills, not from millions of lines of code, but directly from our guidance and our demonstration, what is the very first thing you would teach one?